All right, I think we'll get started. We're still climbing. You've got a good audience here, Klara and Peter. Welcome everyone to the final Minnesota Geological Survey Seminar of the spring semester. And as most of you know, this was a recent addition to the schedule. It was suggested by Sarah Titus from Carleton College. We have two speakers here. We have Klara Kjome-Fisher and Peter Bergenross, and they're both, I assume, seniors. These were your senior projects, right? Seniors at Carleton College, both of whom worked on the Pine Bend impact structure, which some of you may have heard about through talks given by Julia Steenberg here at MGS. And just for a tiny bit of background, before coming to Carleton, Klara lived in Portland, Oregon, and Peter lived in New Haven, Connecticut, if I got that right. I didn't write that one down. All right. These talks will be shorter than our normal talks. If I understood Sarah correctly, they'll be 12 minutes each or 15 minutes each, something like that. They're based on the talks that Peter and Klara gave to their fellow students and professors at Carleton College here recently. So, and I didn't ask which one's going first, but whoever's going first, just go ahead and share your slides and get started.
Awesome. Thank you for the introduction. Today I'm going to talk about deformation features that I found in the Mount Simon Sandstone in a core taken of the Pine Bend impact structure. So many of you may be familiar with the Pine Bend impact structure. It's a structure in Inver Grove Heights, Minnesota, so a little bit east of St. Paul, about 4.5 kilometers in diameter, although my colleague Peter will talk more about that later. It is an impact in the Jordan Sandstone, so it's of Cambrian age, which is significant because most of the impacts that we see around this age are actually from the Ordovician, and it's not part of that group of impacts. It was identified by Julia Steenberg at the Minnesota Geological Survey using well logs and identified using shocked quartz also, and so we know that it's an impact crater. So you can see the geologic map in the upper right-hand side shows the approximate outline of the impact structure. And I'm going to now zoom a little bit more into the cross-section shown. So what do we expect to see in this impact core PB1? Well, the stratigraphy in this area is largely flat-lying. It's marine sandstones and shales and limestones, and there's not a lot of faulting. And you're all probably very familiar with the stratigraphy. And so I would expect to see something like this. See from the Mount Simon Sandstone to the Jordan Sandstone, since it impacted into the Jordan, and see through a lot of these units. Instead, though, we see something like this in the impact core, which is the entire section of the core that was recovered is Mount Simon Sandstone. And it's a lot higher up than you'd expect the Mount Simon to be, and also a lot thicker. And then there were 200 feet of an unrecovered loose sand, which is hard to trace to any of the units. So this is what the Mount Simon Sandstone typically looks like. It's largely flat-lying. There's medium to fine sand and silt and also clay that are interbedded between 1 centimeter and a decimeter scale beds. There's some shallow cross-bedding, but most of the stratigraphy is flat-lying. There's also some normal grading and some soft sediment deformation like flame structures that can help find a younging direction. But it's pretty consistent stratigraphy. This is what the impact core looks like. So on the far left, you can see it's about the same stratigraphy. It's identified as the Mount Simon Sandstone by Julia Steenberg, but it's at steep angles. There's a lot of different angles of bedding in the core, and it's traceable to several different groupings of bedding. There's also areas where the bedding is obscured, and so you can't see clear bedding. There's white lines on the core as seen in the far right image, and also contrasts in grain size that don't seem to be correlated with bedding. So here's a summary so far of the impact core. So the borehole first went through glacial deposits, and then 200 feet of core is unrecovered loose sand. And then all of the recovered core is from the Mount Simon sandstone. And there are really unusual features about this. So my question was, what deformation features are in the impact core? Why are they there? And what does that tell us about the Pine Bend impact? First, I'm going to go over a little bit about impact structure formation. So there's 3 stages in an impact. The first lasts only a few milliseconds, and it's the contact and compression stage. So this is when the meteorite hits the Earth, and it sends a shock wave faster than the speed of sound through the material. And so this is where things like compression come from, and shock indicators like shocked quartz come from this stage. The second stage lasts a handful of seconds to a minute, and it's the excavation stage. So as this shockwave passes through, then there's a rarefaction wave that passes through after it that's basically decompressing the material. And so there's a flow of material upward and outward, excavating the shape of the impact crater. And finally, there's the modification stage. This lasts up to about 20 minutes. And so the core collapses inward, the sides fault down. And in an impact crater that's over about 2 kilometers in sedimentary targets, like the Pine Bend impact, or over about 4 kilometers in crystalline targets, then the buoyancy of the rock in the middle, due to rock being removed from above it, outweighs the strength of the target rock, and so it actually uplifts into what we call a central uplift. And so you can often see older stratigraphy in the center because it's been uplifted. And this is what the resulting impact crater looks like. This is a complex crater, so a crater over 2 kilometers in sedimentary rock, just like the Pine Bend impact. You can see the central uplift really clearly, and in the center of that is often a megablock breccia. So this is brecciated pieces that are very large with dikes and fractures and faults, and this is likely where the core comes from. There's also a fallback breccia over the top, so pieces that rain down after the impact is over. Yeah. So what I did was I did a structural survey of the impact core. And I'm going to go through, first I looked at the core in hand sample, and I'm going to go through things that I saw on the core, and then thin sections that I looked at to try to identify what I was seeing. So the first feature that I saw in a few places was very coarse sandstone that seems to cross-cut bedding. And this is a picture of it on the core, on a cut face. So this is a thin section of it. On the left is in plane polarized light, and the right is cross polarized light. The blue color is the epoxy that's holding the sample together. And you can see that the coarse sandstone is clearly visible. There's a much larger grain size and also a calcite cement present in this section that's not present in the matrix rock, which is much finer grained. You can see to the left. So I identified this feature as clastic dikes. So these are formed when coarse sandstone is injected into surrounding sedimentary layers. And it's been observed in other sedimentary target impact structures like the upheaval dome structure in Utah. So feature 2 is there were smooth faces in shale beds, and some have striations to them or interesting rippled surfaces. And these I identified as slicken sides. I could not take thin sections of them because I couldn't take thin sections of the shale, but they're a marker of fault slip along the surface. The third feature that I found was offsets in bedding. And these I identified as faults. I didn't see faults in the thin sections that I took, mainly because they were mostly visible in places with a lot of shale in the beds, and they were identifiable by a single fault plane with a measurable offset along it. Feature 4 was there were a lot of thin white lines on the core. And sometimes there was a visible offset along them or a change in lithology, and sometimes there wasn't. Also, some white lines were very clear, like in the bottom right image, and some of them were a lot more wispy and not continuous around the core. So this is one picture of a thin section of one of these white bands. This is an SEM backscatter image, and so the lighter places are the grains and the dark parts are the matrix. You can see that this band cuts across the image, and it has a much lower porosity, which I found using a program called ImageJ. And there's a smaller grain size, and so there's a lot of crushed grains in it. Zooming in on those crushed grains, this is what I'm talking about. You can actually trace the original grain boundaries for a lot of these grains. So you can tell that it's one grain that's fractured, and there's also fractures that radiate often from contacts with other grains. And that's what the inside of those bands looks like. And finally, there are some bands like this in much finer siltstone, but these are much more wispy bands and a lot thinner. So I identified these as deformation bands with an element of compaction. So these are when deformation is localized not on a fault plane, but on a wider band. And they're characterized by a decreased porosity and a decreased grain size from crushed grains. And there could be offset along these. It was hard to tell. I also saw a different kind of band because not all of the white lines were explained by these alone. This one is more difficult to see, so I'll put the outline up. There's a band of increased porosity found in image J. You can see more of the matrix. And these are dilational deformation bands. This is really cool. I was very surprised to see dilational deformation bands and compactional deformation bands in the same rock because they're from very much opposite causes. And they were characterized by an increased porosity in the deformation bands. Finally, some of the bands showed a measurable offset. So this is an example of one such band. It's hard to tell exactly what direction the offset was in, but in this case, some of the siltstone was dragged into the band a little bit, which suggests this normal orientation. It also had an increased porosity. So these were shear-enhanced deformation bands. And so there was shear localized to a band, but not a single plane like for a fault. And they could have an element of compaction due to the increased or decreased porosity, but it was hard to tell exactly what was causing that decreased porosity. Finally, feature 5, there were areas where there was not clear bedding, and there was shale that looked really swirly in a mixed grain sized rock. And this could also be seen in one of the thin sections. This is in plain polarized light, where the bedding is really unclear on all scales. I identified this as fluidization. So this is shale flowing and deforming during the impact, and it appears to be different from clastic dikes. And I'd love to be able to look at this more. And this also appeared to be different from the soft sediment deformation already present because it was on a very different scale. So here's a summary of the core features. I found deformation bands. There's compactional bands, shear bands, and dilational bands. And also faults, clastic dikes, slick insides, fluidization, and remember those large-scale changes in bedding angle that I talked about at the beginning. So I'm going to put some of these structures into context. First, I wanted to talk about how I found the orientation of some bedding. I looked at the acoustic televiewer log, and so I used WellCAD. Some of you are probably familiar with WellCAD to identify bedding planes, which show up as sinusoids on the acoustic televiewer log, and find the dip and dip direction from these. I found that the vast majority of the sinusoids that showed up in WellCAD were along bedding planes where I could verify them. So I took all of these to be bedding. And I made, with the help of Serratitis, I made stereo nets of different areas of the core. I found that the bedding could be grouped into several main regions in the core that had significantly different bedding orientations from each other. And some in the middle were possibly overturned as identified by Tony Runkle and Julia Steenberg, looking at normal grading and flame structures. So this suggests actually that we're in a megablock breccia. And so each of those regions of different orientation bedding could be a different block. And so this confirms that the core is likely from the central uplift in that megablock breccia. And that explains the really steep bedding that we're seeing. Then I'm going to look at some microstructures and when they might have formed. So the compactional deformation bands probably formed in that first contact and compression stage. So when the shock wave propagated through, making the shock metamorphism, but also compactional bands. The dilational bands likely formed during the excavation stage. So this is when the rarefaction or decompression wave was passing through the material. They also could have formed during the modification stage, but there's a lot more energy in the excavation stage that could have made these bands happen. Finally, remember that 200 feet of unrecovered, just loose sand in the core. I was thinking about this and where it might have come from. We would likely expect there to be a fallback breccia. So that's material that was excavated out of the crater, but then fell back on top of the stratigraphy. And this is really common in impact craters. But what units would that be coming from? The units above the Mount Simon Sandstone and below the Jordan Sandstone, where we'd expect to find a fallback breccia originating from, include the St. Lawrence Formation, the Tunnel City, the Wanawak, and the Eau Claire. And some of these, especially the St. Lawrence and the Eau Claire, have a lot of glauconite and shale, which is just not present in this sand unit. And so it's possible that it could also be a unit unique to the impact structure. This is not unheard of. In the Decorah structure in Iowa, there's a shale formation that was deposited only within the core. And so there could be something like that here. It would be really interesting to do more research on that. So as a summary, I looked at microscale deformation features in the Pine Bend impact structure, and I found that they were formed likely during different stages of the impact. And bedding changes in stratigraphy confirm a location in the central uplift of the crater. And there's a possible unique stratigraphic unit in the center. And there's so much more research to be done on this project, and I'm excited to see what Julia does with it next. And I'd like to thank my advisor, Sarah Titus, and Julia Steenberg, and also everyone else at the Minnesota Geologic Survey that helped me with this research, and everyone at Carleton that helped me learn how to use the scanning electron microscope and do all of that analysis. Thank you.
Klara, that was awesome. So why don't we get started with you, Peter? Thanks again, Klara. That was great.
Yeah, thank you.
Sounds good. Great job, Klara. I'm also going to be presenting on my thesis work. I did a local gravity survey of the Pine Bend impact structure to better understand its size and shape and some of the subsurface properties. I want to start by explaining this image. This is an aerial photo of Inver Grove Heights. And what you can't see in this image is any sort of impact structure or crater. And I'm going to explain how I used gravity to learn more about the Pine Bend impact structure. Ooh. Okay. I want to begin by acknowledging some of the many people who supported me throughout this project, most notably Sarah Titus, my advisor, and Julia Steenberg, who discovered the impact structure. The key takeaways I want you to get away from this talk are that gravity data can be used to map and model the Pine Bend impact structure. Gravity data suggests larger crater dimensions than previously inferred, and gravity data provides new information about the subsurface properties of the impact structure. And I also want to mention that this photo is taken in Inver Grove Heights atop the impact structure. So it's clear that it would be fairly difficult to study from the surface because there's no kind of superficial topography change or anything like that, which is why gravity and other geophysical methods are especially useful in this scenario. I want to give a brief background on these three, on impact cratering, gravity, and the Pine Bend impact structure, just to get everybody on the same page. As Klara explained, impact cratering occurs over three stages. The first is contact and compression. Again, when a projectile initially touches down on the Earth's surface, it propagates a shock wave out from the source, from the point of contact. The second is excavation, when material is thrown out of the area where the contact occurs, and a release wave follows the shock wave and propagates down. The third is modification, where gravity drives crater slumping, faults occur, and the crater floor can rebound in large enough impacts. And then here, the final panel, I have a final structure of a complex crater. And the things that I want to take note of are a lot of fractured bedrock beneath the impact structure, and the large amount of brecciation within the impact structure. And these are important because they reduce the overall density of the bedrock and kind of the whole impact structure compared to the unfractured and unbrecciated bedrock around. A little bit about gravity. All over the surface of the Earth, it's about 9.8 meters per second squared, but it varies on a very small scale on the order of milligauss, which are about a millionth of Earth's total gravity. And these variations are caused by subsurface density contrast. So if you look to this little cartoon, the red dot represents a positive density contrast in the subsurface. And you can see that depending on the magnitude of this density contrast, you might have a positive gravity anomaly of about 2 milligauss. And inversely, if you have a negative density contrast or a negative anomalous density contrast of a buried mass, you might have a negative gravity anomaly associated with it. And a little bit about the Pine Bend impact structure. As Klara mentioned, it was discovered by Julia Steenberg in 2022 using existing geophysical data. It's in Dakota County, and using the sort of overturned and impacted units, it's dated to be around 490 million years old. Given the distribution of the data of the well logs, the drill cuttings, and some of the targeted core, it has inferred dimensions of around 2 kilometers by 4 kilometers. But there's a fair amount of uncertainty you can see highlighted in this red dashed line, especially to the northwest of the crater. And this is all due to the distribution of the data. You can see it's a little more scattered outside of the crater, and within the Mississippi River Valley, it's difficult to collect data, so there's less geophysical data around there. It's also of note that the impact occurred in flat-lying sedimentary stratigraphy, which influences the expected magnitude of a gravity anomaly that we would see from this impact structure. And I want to talk a little bit about the regional gravity. So this is a map of the Bugey anomaly for the state of Minnesota. The Bugey anomaly is a representation of gravity that highlights subsurface density contrasts. And in this map, warm colors such as reds and pink represent high gravity values, and cool colors such as the dark blue show low gravity. And I want to bring your attention to this band of high gravity from the northeast of the state, sort of down to the southeast. And this band of high gravity is representative of the failed mid-continent rift, in which rift basalts, which are more dense than the surrounding sedimentary stratigraphy, are brought closer to the surface and are thus reflected in the Bugey anomaly. And why this matters, if we zoom into Dakota County here, you can see that there's a really strong regional gradient from the northwest to the southeast throughout the whole county. And this regional gradient encompasses a swing of about 100 milligauss. And this regional gradient is so strong that it overwhelms any small signals such that you would expect of the Pine Bend impact structure. So you can see the impact structure is denoted with this yellow diamond, and there's no variation in the Bugey anomaly around it. So there's no negative signal. Negative anomaly. So to try to find a negative anomaly for the Pine Bend impact structure, I completed a local gravity survey to map and model it. In the fall of 2025, I collected 137 new gravity stations, and I compiled 80 regional stations from the Minnesota Geological Survey State Gravity Database. Here are 2 maps of the points I collected and compiled. On the left, you can see the Twin Cities in the north and the Mississippi River coming down the east side of the map. Each black point represents a regional station that I compiled, and the black outline is the currently inferred dimensions and location of the Pine Bend impact structure. On the right, I've zoomed in and added white points, which show each of the stations that I collected. You can see that they're more densely they're more dense in the northern half of the crater, where the land use is more residential. And so I was able to take measurements on more smaller roads. But in the south of the crater and on the east side, it was a little less accessible, especially in the south of the crater. There's more industrial infrastructure, such as the Pine Bend refinery, where it was inaccessible for me to take gravity measurements. What did I find? This is the Bouguer anomaly of the combined data set, and it's a little hard to evaluate as a contour map, so I will also put up this, which is a 3D view of the gravity surface. And what you may notice are high values around 20 milligauss in the northwest, and low values around -5 to -6 milligauss in the southeast. This trend may remind you of the northwest-southeast regional gradient of Dakota County. This was encouraging initially because it showed that the values that I had achieved within my local survey were somewhat reasonable to the regional values that I would expect to see. But it didn't show any negative anomaly that we had hoped to see with the Pine Bend impact structure because this regional gradient was still overwhelming any possible signal. So to remove the regional gradient, I calculated and then I calculated a surface to just the regional data that I had compiled, and I subtracted that from this Bouguer anomaly of the combined data set. So this is the best fit surface. It's a cubic surface, and you can see it encompasses the high values in the northwest and the low values in the southeast, and some of the more variation in between. And if I take the original Bouguer anomaly and I subtract the best fit surface that was calculated just based off the regional gradient, I get the residual Bouguer anomaly, which looks like this. It's a little hard to evaluate this as a surface, given it's so small, but you may immediately see that there's a large negative dip somewhere in this surface. So if I expand this out to be a contour map, this is that same surface. So this is the residual Bouguer anomaly. And there are a few things that I want to highlight in this contour map. The first, that there are closed contours, which show localized anomalous subsurface mass. And these closed contours are exactly kind of where we would expect the Pine Bend impact structure to be. They show a negative anomaly of approximately 1 to 3.5 milligauss, which is reasonable for a small impact structure in sedimentary stratigraphy. And there are 0 values all over the perimeter of this map, which show an effective removal of the regional gradient, showing that the signal that we're seeing is not being influenced by the northwest-southeast trend that has overwhelmed the signal in the past. So a major part of this project was finding a signal for the Pine Bend impact structure at all. And once we felt confident that this signal was truly reflective of the Pine Bend impact structure, given its magnitude and location, I wanted to use gravity data to learn more about the Pine Bend impact structure and its subsurface properties. So the first thing I looked at was crater shape. I took 3 transects through the combined data set to look at how the crater was shaped. And I found that while it was somewhat elliptical, it was roughly bowl-shaped and kind of almost like a sphere. And you can see this the best in the MGS transect, which had the most data encompassed in that transect. You can see that there's a really nice, almost symmetric bowl-shaped, which is what you would expect in an impact structure. The next thing I looked at was the crater size. I used 2 different methods to determine the crater size. And the first was looking at the second vertical derivative. So the second vertical derivative is a method to strongly enhance near surface anomalies. And I'm going to walk through how that works. Say you have a negative anomaly. You can imagine that this red line is just a simple negative anomaly. If you take the first derivative, it doesn't really tell you much. But if you take the second derivative, you can see that it's most strongly positive, or most strongly enhancing where the negative anomaly is most negative. I also want to note that the second derivative is useful in understanding gravity data because where it crosses 0, or where the polarity changes, can be interpreted as the structural edges of the anomalous subsurface mass. And that's kind of shown by these blue dashed lines here. And the polarity of the second derivative indicates the anomaly type. So a negative anomaly should have a positive second derivative, and a positive anomaly would have a negative second derivative. So this is one of the second derivatives I took of the gravity data of the residual Bouguer anomaly. And the main thing to note are these two kind of parallel bands to the east and to the west of the data that I had collected of really dense contours, are clusters of bands. And in these bands, the polarity changes from being positive, sort of surrounding the data I collected, to being negative outside, sort of on the edges of the map. And so I'm interpreting these bands to be the edges of the impact structure, because that where the polarity changes from where the second derivative crosses zero should represent the edges of the structure that's creating the signal in the first place. It's also of note that the values of the second derivative are positive all around the data, which show that it is a basin structure, so it is a negative anomaly that's being recorded. But it is interesting. It's worth noting that you don't see concentrically more positive contours within these two structural edges, which is what you would expect to see looking at the second derivative. So it's not exactly what we would expect, and I kind of attribute that to some of the messiness of gravity data and of sort of dealing with geophysics in general. But I interpret these to be the structural edges, and I took the second vertical derivative in a handful of directions and arrived at crater dimensions of 8 kilometers by 11 kilometers. The second method I looked at was looking at the actual dimensions of the contours from the residual Bouguer anomaly, and I found that the most likely magnitude for the negative anomaly, given a small impact structure in sedimentary stratigraphy, was around 2 milligals, and the dimensions of the contour that would give that anomaly, so this is more of a rougher estimate, are 7 kilometers by 9 kilometers. If we compare these to the currently inferred dimensions of the Pine Bend impact structure, which are 2 kilometers by 4 kilometers, you can see that both of these estimates are a fair bit larger. However, the currently inferred dimensions have a fair bit of uncertainty, which may reconcile some of this difference. The last part of my project was forward modeling. So forward modeling is a method to predict the gravity signal from a known subsurface structure or use the observed signal to infer geometries about subsurface structures. So I used data along the MGS transect, which encompassed 27 points and was the most symmetric transect that I took to do some forward modeling with a software called GravMag. The first thing I looked at was the density contrast, which was pretty exciting because, to my knowledge, there hasn't been a lot of work done to think about the whole density contrast between the Pine Bend impact structure and the surrounding stratigraphy. And I found that a density contrast of negative 0.2 grams per centimeter cubed was the most likely. So here in this figure, this is kind of a snapshot of a forward model. On the lower panel, on the x-axis, you have distance in kilometers and depth on the y-axis. The green rectangle is kind of a simplification of the Pine Bend impact structure with a negative density contrast, and the blue rectangle is additional thickness of quaternary sediments. In the upper panel, I'm comparing the observed gravity, which is the red line, to the calculated gravity, which is the black line. So I experimented with a variety of negative density contrasts for the Pine Bend impact structure and found that a density contrast of negative 0.2 was the best fit between the observed data and the calculated data. I also looked at the dip of the crater walls. And again, so this is the same forward model where the subsurface is on the lower panel and comparing the calculated and observed gravity values is on the upper panel. And I experimented with different types of crater dips or different angles, and I found that a dip of 30 degrees was the best fit between my data and the calculated data. And I've also added into this model a central uplift of 275 meters. The data that I collected was not of high enough resolution to determine a central uplift from the data alone. But other methods, including some of the stuff that Klara talked about, suggests a central uplift. And given the crater size, sort of being a small crater with diameters less than 10 kilometers, a central uplift of 275 meters would be expected. And that central uplift is a fair amount larger than just the offset beds, but there were dark red shales, to my understanding, found fairly high up in the core, and those could be correlated with deeper units. So it's possible that there was an uplift of that magnitude. And I want to compare this geometry to the final structure of a complex crater to show their similarities. Both of them have sort of these dipping walls around 30 degrees and have a central uplift. And so I think the Pine Bend impact structure, the data that I collected, is suggesting that it has characteristic qualities of a complex crater morphology, which is also pretty exciting. So the key takeaways I hope you gathered from this talk are that gravity data can be used to map and model the Pine Bend impact structure. Gravity data suggests larger crater dimensions than previously inferred, and gravity data provides new information about the subsurface property of the impact structure. And that's my talk. I'm happy to answer any
Yeah,
questions.
that was excellent, Peter. Thank you.